This week, as we start exploring geotechnical design concepts, it's important to keep one key principle in mind. Many designs aim to clamp the rock mass together, or at least prevent it from separating along fractures, joints, or faults. Because the tighter the rock is held together, the more it can rely on its own internal strength for support, which is what we often refer to as passive or self-support. When done well, this approach reduces the need for heavy external reinforcement. So, while it might seem like we're about to jump into a completely different topic, just know there's an important reason why we do this.
We're going to go back in time for a moment, right back to ancient Rome. The Romans, known for their engineering brilliance, discovered that one of the most stable structures isn't a wall or a pillar, it's an arch. Why? Because the strength of an arch comes from its shape. Unlike flat structures that rely on vertical supports, an arch is designed to transfer forces along a curved path. When a vertical load is applied from soil, rock, or any overhead structure, that force doesn't act directly downward through a single point. Instead, the curved geometry of the arch redirects the load outward and downward, distributing it along the entire structure and into the ground through the supports at either end. This redirection causes each block, known as a voussoir, to be pushed tightly against its neighbors. In a traditional masonry arch, each voussoir is cut with a slightly tapered shape, wider on the outer edge and narrower on the inner edge. This wedge-like design allows the blocks to press firmly into each other as the load is transferred through the curve. The result is a system where compression increases friction and interlocking between the blocks, effectively clamping the entire structure together. In fact, even without additional load, a well-formed arch can support itself through this balance of internal forces alone. But the system depends on all pieces working together, especially the keystone at the top. The keystone locks the shape in place. If it's removed, the force path is broken, the compression is lost, and the arch can quickly collapse. That's why Roman aqueducts, viaducts, and even doorways have lasted thousands of years, because the arch is essentially nature's way of saying, distribute the load, and you'll stand the test of time.
We still use this shape today, most notably in arched bridges. In these structures, the arch allows the bridge to carry heavy loads by spreading weight across the entire curve. Just like in Roman design, the stress flows along the curve and into the foundations, rather than building up in one spot. If you've ever stood under an old stone bridge or walked across a graceful concrete span, you've experienced this principle in action, as stability through curved stress paths. Now, let's talk about the proportions of the arch, because even the strongest shape can fail if the size or the shape doesn't adequately support a load. For an arch to work well, it's not just about the arch shape. It's also about how wide it is. So, what is a good rule of thumb for a stable arch shape? The arch should be about as high as it is wide. That way, when a load is applied from above, the forces can be shared out evenly between the top of the arch and the supporting sides.
Now, let's consider what happens when the supports or legs of an arch are placed further apart. By increasing the distance between the supports, the way forces travel through the arch begins to change. In a well-proportioned arch, the load applied at the top is carried along the curve and redirected outward and downward into the supports. This path keeps the structure in compression, allowing each block to press firmly against the next and distributing the load efficiently. But when the legs are spaced wide apart, that continuous stress path breaks down. The central part of the arch no longer has a clear way to transfer load into the supports. Instead of flowing through the arch, more of the force acts directly downward at the center, where there's no vertical support beneath it. At this point, the structure is no longer functioning as a true arch. The geometry no longer carries the load. Instead, the center span begins behaving more like a beam. It must now resist bending and tension, which arches aren't designed to do. This shifts the burden to the material itself, relying on its strength and internal bonding to prevent failure. And if the material is weak or the span too wide, the center is likely to sag, deform, or buckle. So the greater the distance between the supports, the less the arch can rely on its shape, and the more it depends on the strength of the material or engineered reinforcement to hold its form. To bring this idea closer to home, let's look at a familiar example. If you needed to change a light bulb on the ceiling, would you feel comfortable standing on a child's desk made of chipboard? Surprisingly, you probably would, especially if the desk is about as high as it is wide. Why? Because the proportions help distribute your weight more evenly across the structure. And while it's not an arch, the way the forces travel through the desk, from the top down and into the legs, mimics the same principle. When something is proportioned well, even weak material can support more than you'd expect. Now let's look at that same light bulb changing scenario, but with one important difference. This time, the ceiling is higher, and directly underneath the light on the ceiling is an adult-sized desk that is also made from chipboard. But unlike the child's desk, this one is much wider than it is tall. It's actually shaped more like a rectangle than a square. Now, if you were to think about standing in the middle of that desk, you'd probably hesitate, and for good reason. The center would likely bow under your weight, and depending on how weak the material is, it might even crack or collapse. That's because your weight is no longer being effectively transferred down through the supporting legs. Instead, it pushes directly down on the unsupported middle. And just like with an arch with a wide base, this creates a zone of tension and bending in the center, something chipboard, a weak composite material, isn't designed to handle without reinforcement.
So how does all of this apply to mining? Well, it applies to both underground and surface mine designs. Let's start with underground mines. In hard rock mining, it's common to see excavations with an arched profile, not by coincidence, but by design. These profiles often mirror the shape of a Roman arch, where the height and the width are kept relatively similar. That balanced ratio helps distribute stress evenly around the excavation, just like in a structural arch. And in most cases, that profile is reinforced with rock bolts that match the profile's proportions. For example, bolts are often installed across the arch as the drive is developed. This helps to clamp the rock mass together as the nearest surface zone will begin to naturally relax into the newly created void and potentially result in less friction or clamping between rock blocks. Therefore, by installing the ground support straight after development, it helps the development maintain compressive stress across the arched profile. It's a proven design principle, using both geometry and reinforcement to help support the ground.
In underground mining, not all excavations follow the standard arched profile. In areas where a wider span is required, for example in intersections, workshops, or large crusher chambers, the roof spans a greater horizontal distance between the sidewalls. This geometry introduces additional challenges. Unlike a standard arch, which evenly redirects compressive forces through its curved shape, a widespan profile creates a larger roof area that's less efficient at naturally redistributing stress. This results in deeper relaxation zones forming in the roof, a greater weight of rock mass acting downward across the unsupported span, and higher potential for tensile or flexural failure at the center of the span. To address these issues, cable bolts are commonly installed as additional support. These are longer and are designed to support more weight in tension, much deeper into the rock mass. So, how do cable bolts actually work? Unlike standard rock bolts, which are designed to clamp fractured rock together near the surface, cable bolts are much longer and work in a very different way. They're installed deep into the rock mass, extending beyond the relaxed or fractured zone and anchored in more competent ground. Once tensioned, they act like suspension cables, not pulling the rock together, but holding it up. Imagine a heavy slab of rock starting to detach from the roof. A cable bolt resists that movement by transferring the load of that slab to more stable ground above, using tensile strength. So instead of trying to lock individual rock blocks in place, cable bolts help suspend and support larger volumes of rock, especially in areas like widespans, where the roof is flatter and spans a greater distance between sidewalls. In these conditions, gravity tries to pull the roof downward and arching can't fully carry the load. That's where cable bolts come in, working in tension to stop rock from falling. It's not about clamping. It's about holding weight.
The same ground control principles used in underground mines can also apply to surface mining, especially when working beneath a moving slope or a low wall, like in coal mines or in-pit dumps. Let's say there's a section of the low wall that's showing signs of gradual movement, and there's a planned excavation or work area directly beneath it. One method to help control this situation could be to limit the width of the excavation around that area, creating a narrow access rather than a broad, open cut. By keeping the excavation span tight, the pressure or weight of the moving low wall can be partially transferred into the surrounding intact ground or dumped material that locks the moving low wall into the adjacent high wall. In effect, this geometry helps provide natural confinement, similar to the way an arched profile in underground mining redistributes load. The ground can act like a buttress, locking the low wall in place and resisting lateral movement, or at least slowing it down. Now, it's important to be clear. This approach does come with trade-offs. It typically slows down production rates, especially by limiting equipment access and therefore load and haul rates. And it absolutely requires detailed geotechnical analysis to confirm whether it's feasible and safe, especially as the width of the span that is excavated does depend on the strength of the material. But in some cases, this method can also offer a practical way to use geometry to help manage slope movement risks in surface excavations. That's it for this week's video. I hope it's given you something to think about, particularly around why arches are more than just a shape, and how the principle of working with the natural flow of stress around an opening can help us make the most of the ground's own interlocking mechanisms. And when we move to wider spans, where the center of the roof starts to act differently, it becomes clearer why we may need additional engineered support, like cable bolts, to hold everything together. Thanks for watching this week, and we'll see you for the next video.